Hello everyone, my name is Serkan. I'm going to present to you our paper VimoClap, a video emotion classification web application. So the initial goal of my research was to obtain the emotion from the videos and then further process it. But I always thought there would be online tools or at least open source code for this task, so I could easily use it, but in the end I couldn't find any. I mean, this task is a very common task. We have videos and multimedia emotion analysis as a task, but none of the papers were available in open source. So I wanted to make it open source. I had to train my own models, and I wanted to take it one step further, but by making this a web application, which would be just click and play. You know, no setup needed, no configuration needed. You don't have to have a GPU. You can just do everything online. So not just programmers, but also everyday users can utilize it. I'll quickly show you what it looks like, and then I'll go to my presentation so that you have a better idea. So this is the Google Colab page. I will share the link at the end. So I have this short sample video that I use, but you can also, the point is you can upload your own videos, or you can link a YouTube video, or you can choose from the sample videos. So this is the sample input video. The volume can be high, yeah? I haven't done this. Right. This doesn't matter because I already ran this before. So this is the input video, very short.
We'll do it live. Do it live! I'll write it and we'll do it live!
So, based on this video, we're trying to get the emotion. This overall, just 1 second. It's a 5-step process. So step 1 downloads the files and installs the requirements. You do this only once. And here it took less than 2 minutes. In step 2, you build the extractors, feature extractors that I will mention soon. So these are various features that are related to the video that we use for the final classification. And we also build a model. Once again, we only have to run this only once. Even then, we can classify many videos, but we just do this one time. So this part took less than 4 minutes. So in 6 minutes, everything is ready. And if you have this code locally, because I also share the files, you just do this. You don't have to do this again and again. And then you just choose your video. You can upload your video in step 3 and 4, or you can link a YouTube video. And then you get many different analysis results that I will mention soon. One is optical character recognition. In this video, there are some optical characters like inside, edition, watch mojo, etc. In the context of this video, they don't matter much. And then we also do a sentiment analysis of this optical character recognition results. So in this case, you can see all the optical characters here, and the sentiment analysis result is neutral because they don't mean much. And then you have automatic speech recognition. So as you can see here, it says we'll do it live, okay, do it live. And sentiment analysis says positive, basically because this only works on the text, yeah? Even though the presenter is shouting, it doesn't give any negative sentiment. So just by looking at the text, this looks pretty positive. And then you have audio classification results. If you remember from the video, there's speech and there's music. So 50% speech, 50% music. And I also present a sample frame. And in the sample frame, you can see the optical characters, and you can also see the faces and the emotion of these faces. So this is 99% angry. All these are used in the final emotion classification, which I will mention in the slides. And just for fun, I added this predicted caption. This is only for the interface, and I don't use it in the final classification. So it says, politician on the morning of the election, which looks okay, but you know, he's a news presenter. And finally, you have the emotion classification results. And the model is pretty confident because of the small data set size. And this is not a multi-label data set. This is a multi-class data set that I'll mention. So it says 100% anger. So this is the model for you to understand what this is. So now I will mention some details. So again, we are interested in the classification of any video into high-level categories such as genre or emotion. The reason I say they're high-level is they're, in my opinion, higher level compared to, say, action recognition. In action recognition, you can only focus on the body and the object interactions. But when you're looking at a genre of a movie, how would you know that a documentary is different than a drama? even as a human, it's very difficult to explain, and at the computer level, it's very complex. And the second objective was to create a click and run online tool. It shouldn't require manual setup or a local GPU. It should be fast and light enough for Google Colab. So in this case, I had to make my model sizes smaller. And this is a continuation paper. The original paper was in Expert Systems with Applications, but I used genres instead of emotions because I had a larger data set with MovieNet, so I could use larger models without overfitting, and we obtained state-of-the-art accuracy results. And then I kind of modified the model. For emotion classification, I had trained it on Ekman 6 dataset, so it has emotions and the videos. So I had to use smaller model because of overfitting, and once again we obtained state-of-the-art results. And because it's a smaller model, it is deployable on Google Colab, and I put the graphical interface with intermediate features. So now I'll get into a bit in-depth details. Once again, emotions, just like genres, are very complex and multifaceted. So note that I'm not referring only to facial emotions. It can be anything. There can be a video without any faces, so we still analyze the emotions. So the existence of an emotion may depend on these following features: the context of each frame, so the visual aspects, if there is a face, the expressions of the face, on-screen text like optical character recognition, the speech and dialogue and the content of this speech and dialogue, audio events, and music. So I use pre-trained features for each one of these aspects. If we were to do this task without any pre-trained features, that means we only use raw frames and audio to get a complex idea of an emotion, and this would require a very large data set, which doesn't exist, and a very large model. Rather than that, there's no need to reinvent the wheel. We already have all these models publicly available with their weights and pre-trained models, so we can just use them in inference mode. We don't need to train them. We can only train a very small neural network and use these features, and this is the whole idea behind this paper. So for the context of each frame, I used CLIP. This is contrastive language image pre-training. This is an image encoder, but some people also adapt it for image captioning. So it understands what's going on in an image. So you can do it frame by frame. For facial expressions, you first need to detect the face. For this I used YOLO face detector, and then followed by a vision transformer for facial expression classifier. To get the on-screen text, I use Paddle OCR. To get the speech and dialogue, I use Whisper ASR, automatic speech recognition by OpenAI. And to get the audio events and music, I use Beats, bidirectional encoder representations from audio transformers. So this is an audio classifier. And then, in case of texts, I further process it, if needed, using a translator and a spell checker. And finally, a Roberto text sentiment classifier. So we process the text for one step further. Very importantly, we do not use the final prediction of these steps. Yeah, otherwise, we lose so much information if we only take the prediction. Rather than that, we took the activations from before the final layer. So this is the most informative layer that's at the end, but it's still not condensed into predictions. These are usually vectors with size of 512, etc. So these are very compact and informative. Because they are compact, I can only train a shallow neural network just to combine them and then obtain the final emotion classification. And the outputs other than OCR and ACR sentiment are sequences. Because OCR and ASR sentiment, you take the whole paragraph and then it gives you a result, whether it's a positive or negative text. But in case of visual aspects, you have one feature per video, or if you have multiple faces, you have even more. And basically you have audio chunks. So these are sequences. So I need to somehow combine them intelligently, and because all the sizes are different, so this is a non-trivial task. But I use multi-head attention. So I took pairs of two, the sequences, and you can see my mouse nice. I use them using multi-head attention, combine them. And for sentiment classifier result, it's only one vector anyway, so there is no need. And in the end, I take the average attention output along the temporal dimension, concatenate everything, feed it to a linear and softmax layer to get the final classification. Since we use pre-trained networks, we can extract these features only once for the dataset and train many models. You know, as a PhD student, time is very important for us. So I don't have to process these over and over again. I processed them once, put them in my hard drive, and during training I can just pull them from the hard drive and train many models. And there's no data pre-processing during training. Overall, the trained model has 11 million parameters. This is the learnable parameters. It uses at most 16 elements per feature, so 16 video frames or 16 audio chunks as input. And it trains in a few hours, which is really cool. For inference, which I've shown you in Google Colab, there is no backpropagation. So the feature extractors run in inference mode. There is no need to train them because they're already trained. So there is no backpropagation, no gradients, no need for extra GPU memory. And then everything fits on a 12 gigabytes GPU on a free-tier Google Colab. You can upload your own videos or you can link a YouTube video, and you can see the results as well as the intermediate steps as I've shown you. So we have our results on the Ekman 6 dataset. 1,637 short videos with equally for training and testing. 6 labels for emotion, anger, disgust, fear, joy, sadness, and surprise. And this is a multi-class dataset, only 1 label per video. And we obtain state-of-the-art results and a good-looking diagonal on the confusion matrix. There's a side project that I overtook, cleaning the dataset. So because the dataset is only 1,600 videos, I literally went through it one by one. It was a long day, and then I found some very problematic videos. So, for example, for anger, and I underlined these search keywords because I can see the file names. So this is only my assumption that how they have been wrongly included in the dataset. For anger, there are videos of just one person acting in an annoying way, so there's nobody to be angry. For disgust category, there are videos only flashing lights. I assume these videos are to induce dizziness or nausea in whoever that's viewing, but again, there is no emotion of disgust in these videos. There are also videos related to boredom and loading. In the category of fear, there is counterterrorism videos, but this is just videos of police force. Underwater footage, 9/11 terrorism attack aftermath, so you just see buildings that are already collapsed, so there is nothing to induce fear. I mean, it's sad, but I wouldn't call it fear. Suspect apprehension. In Joy, which was pretty problematic for me, there's videos of Joyride, just somebody driving a car. Music videos including Beethoven's Ode to Joy, and very weirdly, with videos with people named Joy. So there is not emotion of joy, but just a person named Joy. In sadness, you have pensive. In surprise, you have distraction, and people performing impressive features labeled as astonishing. Once I remove these videos, the accuracy improves a bit, but I wouldn't present this as a quantitative study because the test set also changes, so it's not a fair comparison. So everything is available online. This application you can reach through this link. It has a redirect to Google Colab, so if you go to the link below it, this is the project page, you can find a direct link to Colab as well. And the extracted pre-trained features for the entire dataset and the list of problematic videos are on Zenodo. So in conclusion, we do video emotion classification on the Ekman 6 dataset, and we obtain state-of-the-art accuracy results. We made a publicly available click and run online tool for video emotion classification that you can upload your own videos or link YouTube videos. And finally, we did a manual inspection and cleaning of the Ekman 6 dataset. I included the references in case you want to go through them later. And that's it. Thanks for listening, and I'm open for any questions.
Okay, let's take the speaker. We have time for one question, one small question. Is there any questions from the audience or online?
Thank you for the presentation. I have a question about the inference. Do you have like some inference time?
Yes, so it depends on the video, of course. But I did some experiments, and for a 60-second video, it took like 30 seconds on average. But if your video has long dialogues or lots of OCR characters, if the process text is long, it takes longer. But if you have the source code and if you train your own models, you can easily exclude these features, losing a bit of accuracy in return for speed. But in general, it's like half of the time of the video.
And with regard to the actual input to the model, are you doing some like tiling the sequences, or is it?
Sorry, can you repeat?
Are you cutting the video into smaller sequences, or is it like processing frame by frame and then the audio as like a whole? Or
So with audio, I take chunks, and like 1 second chunks or maybe 3 second chunks, I cannot remember well. And frames are frames. And the inputs are 16 elements, so it's 16 frames or 16 audio chunks and the entire text. This works well for the case of overfitting because during training I can do data augmentation by randomly selecting these frames and chunks. And at test time I take them equally spaced to cover the entire video. But if you go to this other paper, like the main paper in an expert journal paper, there I use all of the data. I use all the frames, I use all the audio because I have many more videos. So there's way less overfitting, so I can use more. But in this case, I had to use less because of overfitting.
all right, thank you.